Section 1.6, Absolute Value Functions. Learning Objectives. In this section you will 1. Graph an absolute value function. 2. Solve an absolute value equation. 3. Solve an absolute value inequality. Figure 1. Distances in deep space can be measured in all directions. As such, it is useful to consider distance in terms of absolute values. Credit. S58Y, Flickr. Until the 1920s, the so-called spiral nebulae were believed to be clouds of dust and gas in our own galaxy, some tens of thousands of light-years away. Then, astronomer Edwin Hubble proved that these objects are galaxies in their own right, at distances of millions of light-years. Today, astronomers can detect galaxies that are billions of light-years away. Distances in the universe can be measured in all directions. As such, it is useful to consider distance as an absolute value function. In this section, we will investigate absolute value functions. 1.6.1. Understanding absolute value. Recall that in its basic form f of x equals the absolute value of x, the absolute value function is one of our toolkit functions. The absolute value function is commonly thought of as providing the distance the number is from 0 on a number line. Algebraically, for whatever the input value is, the output is the value without regard to sign. A. Absolute value function. The absolute value function can be defined as a piecewise function. F of x equals the absolute value of x equals x if x is greater than or equal to 0 equals negative x if x is less than 0. Example 1. Determine a number within a prescribed distance. Describe all values x within or including a distance of 4 from the number 5. Solution. We want the distance between x and 5 to be less than or equal to 4. We can draw a number line, such as the one in Figure 2, to represent the condition to be satisfied. Figure 2. The distance from x to 5 can be represented using the absolute value as the absolute value of x minus 5. We want the values of x that satisfy the condition. The absolute value of x minus 5 is less than or equal to 4. B. Analysis. Note that negative 4 is less than or equal to x minus 5. 1 is less than or equal to x. X minus 5 is less than or equal to 4. X is less than or equal to 9. So the absolute value of x minus 5 is less than or equal to 4 is equivalent to 1 is less than or equal to x is less than or equal to 9. However, mathematicians generally prefer absolute value notation. Try it. Number 1. Describe all values x within a distance of 3 from the number 2. Example 2. Resistance of a resistor. Electrical parts, such as resistors and capacitors, come with specified values of their operating parameters, resistance, capacitance, etc. However, due to imprecision in manufacturing, the actual values of these parameters vary somewhat from piece to piece, even when they are supposed to be the same. The best that manufacturers can do is to try to guarantee that the variations will stay within a specified range, often plus or minus 1%, plus or minus 5%, or plus or minus 10%. Suppose we have a resistor rated at 680 ohms with plus or minus 5%. Use the absolute value function to express the range of possible values of the actual resistance. Solution. 5% of 680 ohms is 34 ohms. The absolute value of the difference between the actual and nominal resistance should not exceed the stated variability, so, with the resistance R in ohms, the absolute value of R minus 680 is less than or equal to 34. Try it. Number 2. Students who score within 20 points of 80 will pass a test. Write this as a distance from 80 using absolute value notation. 1.6.2. Graphing an absolute value function. The most significant feature of the absolute value graph is the corner point at which the graph changes direction. This point is shown at the origin in Figure 3. Figure 3. X, Y. Y equals the absolute value of x. Figure 4 shows the graph of y equals 2, the absolute value of x minus 3 plus 4. The graph of y equals the absolute value of x has been shifted right 3 units, vertically stretched by a factor of 2, and shifted up 4 units. This means that the corner point is located at 3, 4, for this transformed function. Figure 4. Y equals the absolute value of x. Right 3. Y equals the absolute value of x minus 3. Vertical stretch. Y equals 2, the absolute value of x minus 3. Up 4. Y equals 2, the absolute value of x minus 3 plus 4. Example 3. Writing an equation for an absolute value function. Write an equation for the function graphed in Figure 5. Figure 5. X, Y. Solution. The basic absolute value function changes direction at the origin, so this graph has been shifted to the right 3 units and down 2 units from the basic toolkit function. See Figure 6. Figure 6. X, Y. 3, negative 2. We also notice that the graph appears vertically stretched, because the width of the final graph on a horizontal line is not equal to 2 times the vertical distance from the corner to this line, as it would be for an unstretched absolute value function. Instead, the width is equal to 1 times the vertical distance as shown in Figure 7. Figure 7. Ratio 2 over 1. Ratio 1 over 1. 3, negative 2. From this information we can write the equation. F of x equals 2, the absolute value of x minus 3, minus 2, treating the stretch as a vertical stretch, or f of x equals the absolute value of 2 times, open parenthesis, x minus 3, closed parenthesis, minus 2, treating the stretch as a horizontal compression. A. Analysis. Note that these equations are algebraically equivalent. The stretch for an absolute value function can be written interchangeably as a vertical or horizontal stretch or compression. Q and A. If we couldn't observe the stretch of the function from the graphs, could we algebraically determine it? Yes. If we are unable to determine the stretch based on the width of the graph, we can solve for the stretch factor by putting in a known pair of values for x and f of x. F of x equals A, the absolute value of x minus 3, minus 2. Now substituting in the point, 1, 2. 2 equals A, the absolute value of 1, minus 3, minus 2. 4 equals 2a. A equals 2. Try at number 3. Write the equation for the absolute value function that is horizontally shifted left 2 units, is vertically flipped, and vertically shifted up 3 units. Q and A. Do the graphs of absolute value functions always intersect the vertical axis? The horizontal axis? Yes, they always intersect the vertical axis. The graph of an absolute value function will intersect the vertical axis when the input is 0. No, they do not always intersect the horizontal axis. The graph may or may not intersect the horizontal axis, depending on how the graph has been shifted and reflected. It is possible for the absolute value function to intersect the horizontal axis at 0, 1, or 2 points. See Figure 8. Figure 8. A. The absolute value function does not intersect the horizontal axis. B. The absolute value function intersects the horizontal axis at 1 point. C. The absolute value function intersects the horizontal axis at 2 points. 1.6.3. Solving an absolute value equation. Now that we can graph an absolute value function, we will learn how to solve an absolute value equation. To solve an equation such as 8 equals the absolute value of 2x minus 6, we notice that the absolute value will be equal to 8 if the quantity inside the absolute value is 8 or negative 8. This leads to two different equations we can solve independently. 2x minus 6 equals 8. 2x equals 14. X equals 7. Or 2x minus 6 equals negative 8. 2x equals negative 2. X equals negative 1. Knowing how to solve problems involving absolute value functions is useful. For example, we may need to identify numbers or points on a line that are at a specified distance from a given reference point. An absolute value equation is an equation in which the unknown variable appears in absolute value bars. For example, the absolute value of x equals 4. The absolute value of 2x minus 1 equals 3. The absolute value of 5x plus 2 minus 4 equals 9. A. Solutions to absolute value equations. For real numbers a and b, an equation of the form, the absolute value of a equals b, with b, is greater than or equal to 0, will have solutions when a equals b, or a equals negative b. If b is less than 0, the equation, the absolute value of a equals b, has no solution. How to? Given the formula for an absolute value function, find the horizontal intercepts of its graph. 1. Isolate the absolute value term. 2. Use the absolute value of a equals b to write a equals b, or negative a equals b, assuming b is greater than 0. 3. Solve for x. Example 4. Finding the zeros of an absolute value function. For the function f of x equals the absolute value of 4x plus 1 minus 7, find the values of x such that f of x equals 0. Solution. 0 equals the absolute value of 4x plus 1 minus 7. Substitute 0 for f of x. 7 equals the absolute value of 4x plus 1. Isolate the absolute value on one side of the equation. 7 equals 4x plus 1, or negative 7 equals 4x plus 1. Break into two separate equations and solve. 6 equals 4x. X equals 6 over 4 equals 1.5. Negative 8 equals 4x. X equals negative 8 over 4 equals negative 2. The function outputs 0 when x equals 1.5 or x equals negative 2. See Figure 9. Figure 9. X, y. F. Negative 2, 0. X, where f of x equals 0. 1.5, 0. X, where f of x equals 0. Try it number 4. For the function f of x equals the absolute value of 2x minus 1 minus 3, find the values of x such that f of x equals 0. Q and A. Should we always expect two answers when solving the absolute value of a equals b? No, we may find 1, 2, or even no answers. For example, there is no solution to 2 plus the absolute value of 3x minus 5 equals 1. How to? Given an absolute value equation, solve it. 1. Isolate the absolute value term. 2. Use the absolute value of a equals b to write a equals b, or a equals negative b. 3. Solve for x. Example 5. Solving an absolute value equation. Solve. 1 equals 4, the absolute value of x minus 2 plus 2. Solution. Isolating the absolute value on one side of the equation gives the following. 1 equals 4, the absolute value of x minus 2 plus 2. Negative 1 equals 4, the absolute value of x minus 2. Negative 1 over 4 equals the absolute value of x minus 2. The absolute value always returns a positive value, so it is impossible for the absolute value to equal a negative value. At this point, we notice that this equation has no solutions. Q and A. In example 5, if f of x equals 1 and g of x equals 4, the absolute value of x minus 2 plus 2 were graphed on the same set of axes, would the graphs intersect? No, the graphs of f and g would not intersect, as shown in figure 10. This confirms, graphically, that the equation 1 equals 4, the absolute value of x minus 2 plus 2 has no solution. Figure 10. F of x equals 1. G of x equals 4, the absolute value of x minus 2 plus 2. Try it number 5. Find where the graph of the function f of x equals negative the absolute value of x plus 2 plus 3 intersects the horizontal and vertical axes.